We're going to talk about some solving logarithmic and exponential equations, and just some of the things that we can do uh, to work on solving these. Now, with this question, for example, we have a couple of options. We could rewrite this one as log base 8 of 8 and then simplify the right-hand side, and then we would be able to just drop the logarithms. However, it might be easiest for us to start off by adding log base 8 of x plus 4 to both sides. Because let's look at what happens. First off, our right-hand side is now just the number 1. Our left-hand side, we're adding logarithms together. So we're adding exponents, which means we can rewrite this as log base 8 of x plus 6 times x plus 4. Okay. Then, using the definition of what a logarithm is, we can rewrite this to be x squared plus 10x plus 24 equals 8. Because, of course, this is saying 8 to the first power equals x plus 6 times x plus 4. And then to finish solving this, we can subtract 8 from both sides to end up with x squared plus 10x plus 16. And now we're just having to ask ourselves questions like, okay, well, what can multiply to give me to 16 to add to 10 if I want to try to factor it? Or more to the point, it's probably going to be easier to either complete the square or to use the quadratic formula. So I'm going to use completing the square here in a second, because for the quadratic formula you just have to remember what it is. And that is this thing up here. Opposite b plus or minus the square root of b squared minus 4ac all over 2a. This is our quadratic formula. We can use it to solve this because we would treat a is equal to 1, b is equal to 10, and c is equal to 16. Let's solve this using completing the square, though. So, if you recall, the first step of completing the square is to, since we already have a 1 in front of our x squared, is to take half of our b term, which in this case is 5. We're going to square it, and we're going to add it and subtract it. The reason that we add it and then subtract it is so that we don't change anything. So now over here on my setup, this part is going to simplify down by design into x plus 5 squared. And then 5 squared being 25, I have 16 minus 25, which is going to leave me with negative 9. So then, at this point, we would add 9 to both sides of our equation, ending up with x plus 5 squared is 9. Take the square root of both sides. X plus 5 equals plus or minus 3. and then subtracting 5 from both sides, leaving us with x equals negative 5 plus or minus 3, which we could also just have as meaning that x is either negative 2 or negative 8. So we then just have to go up here and plug in to see which one works. Well, instantly, if I plug in negative 2, I can take log base 8 of 4, so negative 2 would give me log base 8 of 4 equals 1 minus log base 8 of 2, which we can calculate and figure out kind of what's going on here. In fact, without even having to figure out what the log base 8 of 4 is, I know that 1 is log base 8 of 8. So log base 8 of 4 is equal to log base 8 of 8 minus log base 8 of 2. And we know that if we are subtracting exponents, that means that we divided. So this is actually log base 8 of 4 on both sides of my equation. So 2 works. However, if I put negative 8 into this, I get log base 8 of negative 2 and log base 8 of negative 4, which cannot happen. So the only possible answer here is x equals negative 2. Okay, let's move on to a second example. This one's different, but it's, again, if it's just that we take our time and we identify what's going on, it becomes relatively straightforward. And since we are squaring this log base 3, it actually changes a lot of the stuff that we would normally do. It becomes very difficult for us to combine these into a single logarithm. But let's notice something. We have log base 3 of x squared minus 3 log base 3 of x, and I'm going to write minus 10 equals 0. Now, two numbers that add to give me negative 3, but multiply to give me negative 10 are negative 5 and positive 2, which means that this thing here, this expression, simplifies down to log base 3 of x minus 5 times log base 3 of x plus 2. Okay. And both these things multiply to give me 0, which means that I either have log base 3 of x minus 5 equals 0, or log base 3 of x plus 2 equals 0. In this first case, we're looking at x equals 3 to the 5th. In this second case, we are looking at x equals 3 to the negative 2. So our first case, 3 to the 5th is 3 to the 4th times 3, and 3 to the 4th is 81. 81 times 3 is 243. So we have 243 over here for my x. And over here for my y, my second one, I have x equals 3 to the negative 2 power, which is really just x equals 1/9. And here's my two possible answers. We can try them out. And if I take 243 and put it in here, so what we get is log base 3 of 243. Well, log base 3 of 243 is 5. Meaning we technically could have just said log base 3 equals 5, or log base 3 equals negative 2. But we do want to know what our x's are in the end. So 25 minus 15 does equal 10. But also 4 plus 6 equals 10. So when we plug these values in for our x, we get two things that work. So both of these solutions are viable. We're going to look at one more, and this one's an exponential function. Now, we have e to the 2x equals x plus 2. And honestly, the easiest thing for us to do is to take the natural log of both sides of our equation. So this would be the natural log of e to the 2x equals the natural log of x plus 2. And we could move everything over to one side of our equation. And this would give us the natural log of e to the 2x divided by x plus 2 equals 0. And of course, when the natural log equals 0, this thing equals 1. And you're I'm sure by now you're actually seeing what's going on. We've actually gone in a circle. So, maybe this isn't the best route for us to take. Which means we need to think of a possible alternative. Well, let's see. E to the 2x. That is the same thing as e squared to the x power. Okay, and we know that that has to equal x plus 2. Well, if we were to consider log base e squared, so log base e squared, what does that give us? That gives us log base e squared of x plus 2 is equal to x. Okay, does that help us at all though? Not really. And now you're probably starting to see some of the disadvantages of trying to solve these expressions, because we have to figure out a good way of doing so. Okay, well, let's see. One way that we could do this would be to graph it and see where these two things intersect. And that's probably going to be the easiest route for us to take here. So let's go and do that. So what we're going to do is we're going to go over to Desmos, just so that we can see everything here. We could, of course, graph this on our graphing calculators, but let's see what happens. So we have e to the 2x, and it might help if I actually put e in. And if I go e to the 2x, and then I graph x plus 2, we see that it crosses at 2 locations. Because we definitely intersect down here at x is negative 1.981, and then the other place that we intersect is up here, which is at 0.448. So that would be one of our ways to figure out what this equals. Now, if we were using something like Desmos, we don't have to separate it like this. If we're using a TI-84, we do have to write it as two separate functions and see their intersection. But if we're using Desmos, we can actually do something, or should be able to do something like this. And we see that we have two possible values for x. And one of those possible values is over here, which if we can kind of zoom in, we can see that it's about the same thing that we thought it would be, and over here the same. If you want to get an exact, you could always just say x equals, not x equals 0, y equals 0. Because what has happened now that we have y equals 0, we have the intersection of the two. And we can see that they intersect exactly where we thought they would. Okay. And that will do it for this video, and I will see you in